On two separate nights in December, telescopes on Earth recorded something unusual on the surface of the moon. For less than a second, a brief flash of light appeared on the moon's dark side, bright enough to be detected from roughly 384,000 kilometers away. There was no plume rising into space, no lingering glow, and no visible aftermath at the time, just a momentary burst of light and then darkness again. These flashes were not artistic impressions or camera errors. They were recorded, time-stamped, and measured. What makes them scientifically interesting is not that something hit the moon, because impacts happen there all the time, but that such small objects could produce flashes visible across the Earth-Moon distance. The immediate question was not one of danger or spectacle, but of scale. The objects responsible were likely no larger than a few centimeters across, comparable to a golf ball. Yet the light they produced was strong enough to stand out against the lunar night. That contradiction sits at the center of this investigation. Tiny objects should not, by intuition alone, create effects visible from Earth, and yet, under the right conditions, they clearly can. The explanation begins with speed. Objects moving through interplanetary space do not travel slowly. When a small meteoroid strikes the moon, it often does so at tens of kilometers per second. At those velocities, mass matters far less than motion. Energy increases with the square of speed, so even a pebble can carry an enormous amount of kinetic energy if it is moving fast enough. When that energy is released all at once on impact, it is converted almost instantly into heat and light. What was directly observed in December were flashes lasting fractions of a second. What must be inferred are the size, speed, and mass of the impactors that caused them. Scientists are careful to separate those two categories. The flashes themselves are confirmed observations. The characteristics of the impacting objects are derived from models and previous measurements. The timing of the events added another layer of interest. The two flashes occurred within the same week, during a known period of elevated meteoroid activity. That raised a deeper question. Were these impacts random, or were they linked to a specific stream of debris moving through the Earth-Moon system at that time? Answering that requires context, history, and careful comparison with decades of prior observations. Systematic monitoring of lunar impacts did not begin recently. Although astronomers had long suspected that meteoroids regularly strike the moon, dedicated observation programs only became practical in the late 1990 seconds. Advances in sensitive digital cameras and automated detection software made it possible to continuously monitor large portions of the lunar night side. Beginning around 1999, teams in multiple countries started recording hours of lunar video, later scanning it frame by frame for sudden flashes. Over the years, this method has produced hundreds of confirmed detections. Most of them are found after the fact. Software flags a sudden change in brightness, and researchers then verify that it is not caused by cosmic rays, satellite reflections, or camera noise. Seeing an impact live, as it happens, is far less common. It requires the right telescope pointed at the right region of the moon at the exact moment an impact occurs. The December detection stood out partly because one of them was observed in real time by an astronomer watching a live feed. That alone makes it unusual, but not unprecedented. What drew more attention was the clustering of events. One flash was recorded on December 12, another occurred on December 19. Both were detected on the moon's night side, and both were described as relatively bright compared to typical lunar impact flashes. When researchers placed these dates on a calendar of known meteoroid activity, a pattern emerged. Mid-December is the peak period of the Geminid meteor shower, one of the most reliable and intense annual meteor showers observed from Earth. The Geminids are active from early to late December, with maximum rates around the 13th and 14th. The December 12 flash occurred just before this peak, and the December 19 event fell shortly after it. This timing does not prove a connection, but it immediately suggested one. Looking back through historical data adds perspective. Since monitoring began, roughly 600 to 700 lunar impact flashes have been confirmed. Only a small fraction are associated with known meteor showers, but when they are, the correlation tends to be statistically meaningful. One of the most famous examples occurred in September 2013, when a large impact on the moon produced a flash visible for several seconds. That event was later confirmed by orbital images showing an 18-meter-wide crater at the impact site. Compared to that, the December flashes were modest. They lasted less than a second and implied impactors weighing perhaps only a few hundred grams at most. Still, within the context of decades of observations, two bright impacts within a single meteor shower window naturally raise scientific interest rather than alarm. Understanding what these flashes represent requires a closer look at the physics involved. When a meteoroid strikes the moon, it does so without atmospheric interference. The moon has only a trace atmosphere, so thin that it offers virtually no resistance. An object approaching the moon at 30 to 40 kilometers per second will hit the surface at nearly that same speed. On Earth, the situation is very different. Incoming meteoroids encounter dense air, which compresses and heats rapidly, causing most objects to burn up high in the atmosphere. By the time a meteorite reaches the ground, if it reaches the ground at all, it has lost nearly all of its original kinetic energy. The bright streaks seen in Earth's sky are atmospheric phenomena, not surface impacts. On the moon, the energy release happens at the surface itself. The moment of impact generates extreme temperatures, often estimated between 2,000 and 5,000 degrees Celsius in the immediate impact zone. These values are not measured directly but are inferred from models of hypervelocity impacts tested in laboratories and compared with known crater characteristics. The impact vaporizes both the meteoroid and a small amount of lunar surface material, creating a rapidly expanding cloud of superheated plasma and debris. That cloud emits light as it cools, producing the flash detected by telescopes on Earth. The brightness and duration of the flash depend on several factors, including impact, speed, angle, and material composition. For the December events, models suggest impact velocities of around 35 kilometers per second, equivalent to roughly 78,000 miles per hour. At that speed, even a 1 to 3 centimeter object can release energy comparable to tens of kilograms of explosive material. Estimates for similar events place the energy release in the range of 50 to 100 pounds of TNT. These comparisons are used only as a way to communicate scale. No explosion occurs in the chemical sense. The energy comes purely from motion converted into heat and light. The resulting crater is typically a few meters across, surrounded by a blanket of fine ejecta. In most cases, these craters are too small to be resolved from Earth and can only be confirmed by lunar orbiters under favorable lighting conditions. There are important uncertainties in all of these estimates. The exact size and mass of the impactors cannot be measured directly from a flash alone. Scientists work backward from brightness and duration using assumptions based on previous impacts and laboratory experiments. Composition also matters. A dense metallic object behaves differently on impact than a porous, rocky one. For that reason, impact energy ranges are always given with margins rather than precise values. This is where the data becomes unclear. The flashes tell researchers that an impact occurred and give clues about its energy, but they do not uniquely identify the object that caused it. That identification depends on context, timing, and statistical association. This is where the Geminid meteor shower becomes central to the discussion. The Geminids are unusual among meteor showers because they are associated not with a classic icy comet, but with an object known as 3,200 Phaethon. Phaethon is about 6 kilometers in diameter and follows an orbit that brings it closer to the Sun than any other named asteroid. At its closest approach, it comes within about 0.14 astronomical units of the Sun, roughly 21 million kilometers. For comparison, Mercury orbits at an average distance of 0.39 astronomical units. Phaethon's surface temperature at perihelion is estimated to reach around 750 degrees Celsius. At those temperatures, some minerals can fracture, crack, or release trapped gases. Phaethon behaves in ways that blur the line between asteroid and comet. It does not show a traditional dust and ice tail, but observations have revealed a faint tail composed largely of sodium gas when it approaches the sunday. This suggests active mass loss, though the mechanism is still debated. One interpretation is that intense solar heating causes thermofracturing, gradually shedding material that spreads along Phaethon's orbit to form the Geminid debris stream. Another interpretation is that Phaethon is the remnant of a much larger object that fragmented in the distant past, perhaps through collision or rotational breakup. In this view, the Geminids are the lingering debris of that ancient event. Here is what scientists agree on. The Geminid meteoroids have well-measured orbits that trace back to Phaethon. Their velocities relative to Earth and the Moon are high, which matches the energy required to produce bright lunar impact flashes. The timing of the December impacts aligns closely with the period when the Geminid stream intersects the Moon's orbit. What remains uncertain is the detailed history of Phaethon itself. Is it a rocky asteroid that behaves like a comet under extreme solar heating, or is it something transitional that does not fit neatly into either category? That question remains open, and different research groups emphasize different mechanisms based on available data. Speculation exists, but it is constrained. Some studies explore whether Phaethon could be a fragment of a larger parent body that broke apart thousands of years ago, producing a family of related objects. Others focus on ongoing processes, suggesting that each close pass to the sun releases fresh material. What is not supported by evidence are claims that Phaethon is artificial or anomalous in a non-natural sense. All observed behaviors, while unusual, fall within known physical processes. The December lunar impacts do not resolve this debate, but they add data points. Each confirmed impact associated with the Geminids helps refine models of particle size distribution, impact frequency, and energy. Looking ahead, scientists have clear plans to test their interpretations. One of the most important steps is to search for the craters left behind by these December impacts. Lunar orbiters such as the Lunar Reconnaissance Orbiter routinely image the Moon's surface at high resolution. By comparing images taken before and after the impact dates, researchers can sometimes identify fresh craters based on changes in reflectivity and shape. This process depends on lighting conditions. The region where the flash occurred must be illuminated by the sun at a favorable angle for shadows to reveal surface features. If a crater is found at the expected location, its size can be measured directly. That measurement provides an independent check on energy estimates derived from flash brightness. Future monitoring efforts will also focus on timing. When meteor shower peaks are known in advance, observers can prioritize lunar monitoring during those windows. This increases the likelihood of detecting impacts and improves the statistical link between specific debris streams and lunar events. Over time, this builds a more accurate picture of how often the Moon is struck by objects of different sizes and speeds. That information feeds directly into models used to assess risk for future lunar missions. This matters because human activity on the Moon is set to increase. Plans to establish long-term lunar habitats, particularly near the South Pole, require detailed knowledge of the micrometeoroid environment. Studies suggest that the Moon is struck by hundreds of small meteoroids each day, many no larger than grains of sand or small pebbles. Individually, these impacts pose little threat to a well-designed habitat, but over long durations, they become a design consideration. Modern shielding uses layered materials that break up incoming particles before they can penetrate critical structures. Designing that shielding correctly depends on knowing impact rates, velocities, and compositions with reasonable accuracy. The December flashes, taken alone, do not change our understanding dramatically. They are not warnings or anomalies in the sense of unexpected danger. What they represent is the steady accumulation of evidence. Each confirmed impact refines models and reduces uncertainty. This is how planetary science advances, not through single dramatic discoveries, but through careful measurement repeated over years and decades. Small observations add up. The Moon, lacking in atmosphere, records the activity of near-Earth space in a way that Earth itself cannot. Every flash on its surface is a data point about the environment through which our planet and its satellite move. What is known is clear. Small, fast-moving objects regularly strike the Moon. Under the right conditions, those impacts produce flashes visible from Earth. Some of these impacts are associated with known meteor showers and their parent bodies. What remains under study are the details. How exactly does an object like Phaethon evolve over time? How stable are its debris streams? How does impact frequency vary over years or centuries? These are open scientific questions, not mysteries in the dramatic sense, but problems to be solved through continued observation and analysis. The broader takeaway is one of perspective. The moon may appear static and unchanging, but it is constantly interacting with its environment. Brief flashes on its surface reveal an ongoing exchange of energy between planetary bodies and interplanetary debris. By studying these events carefully, scientists gain insight not only into the moon's surface, but into the dynamic system that surrounds Earth. Curiosity, guided by evidence and tempered by uncertainty, remains the most reliable tool for understanding that system.